in previous class, I discussed about basic definitions and different classifications of transformer. And now in this class, I am going to discuss different use of principle of transformer and continuous of transformer and working of the transformer and some applications of inductive transformer. Okay, first I will start with the principle of inductive transformer. So the transformer works on the principle of mutual inductance. You are already said that in the previous class. The transformer works on the principle of mutual inductance. So it transfers an electrical energy from one circuit to another. You already know this point. So it transfers an electrical energy from one circuit to another. Then there is no electrical connection between the two circuits. Okay. There is no electrical connection between the two circuits. By using mutual inductance, you will transfer the energy. So the principle of mutual inductance states that when three coils are inductively coupled, okay, when the three coils are inductively coupled and its current in one coil is changed uniformly, then EMF gets into the other coil. So this is the statement of the mutual inductance. So what is the statement of mutual inductance? When two coils are inductively coupled, so when the two coils are inductively coupled and current in one coil is changed uniformly, then EMF gets into the other coil. Okay, this EMF can drive this current. Okay, then it flows for power to it. This EMF drives the current, then it flows for power to it. So the transformer works on the same principle like mutual inductance. Okay, so in its elementary form, it consists of two electric wires. Okay. So in its elementary form, that is the primary fundamental, it consists of two inductive coils. So having high mutual inductance, So this is the basic transformer diagram. Okay, the basic transformer is in the diagram. So if you see on the left side of this diagram, we have the transformer connection. Okay, so that is a transformer. It is in a rectangular shape, and in those the rectangular is called a core. Okay, and it consists of two windings. On the right side, on the left side we have one winding, and on the right side we have one winding. So the left side winding is connected to the supply, is called primary winding, and the winding on the right side is connected to the load is called secondary winding. Okay, and it consists of number of turns. The primary winding consists of N1 turns, and the secondary winding consists of N2 turns, and it consists of laminated magnetic iron core. Okay, and next, so in between the windings we have some dotted lines. So those dotted lines is also called as flux lines. Okay, and we have two waveforms. So one is for the primary voltage and another is for the secondary voltage. Both of them are aware that DBS is used in supply. So if you observe the diagram, so the primary winding is connected to the AC supply only. Not the DC is connected to the AC. That means the transformer works on the AC supply. Okay. So here in both the waveforms, there is no change in the frequency, but only change in the voltage. Only the voltage level changes, but frequency remains constant. That is, frequency is also constant. So this is the principle, and coming to the next one, the principle of transformer. So actually, I said that actually we have the two coils. So one of the two coils is connected to a source of alternating voltage. That is the primary winding. Everybody coil is put right here. Okay. So one of the two coils is connected to a source of alternating voltage. So this coil emits electrical energy that is to the help of source. Okay. This coil emits electrical energy that is with the help of source is called primary winding. Okay, next the other winding is connected to the load. So the other winding is connected to the load. So electrical energy transferred to this winding is drawn out to the load. Okay, the electrical energy transferred to this winding is drawn out to the load, and this winding is called the secondary winding. So I already said that the winding is connected to the alternating supply. So that is known as primary winding, and the winding is connected to the load is called secondary winding. Okay, next the primary winding has N1 number of turns and the point also, while the secondary winding has N2 number of turns. Okay, N2 number of turns. So this is the symbolic representation. So if you observe the symbolic representation of the basic transformer, so on the left side we have P and on the right side we have S, that is primary winding and secondary winding. So the primary winding consists of N1 turns and the winding is sent to the supply. So that is the AC supply is the primary winding, and the winding is connected to the load that is on the right side of the diagram. That one is known as secondary winding, and the secondary winding consists of N2 number of turns, and the two vertical lines in between the primary and secondary winding is called core, magnetic core or core of the transformer. Okay, so this is the symbolic representation of transformer. And next, so when the primary winding is excited by an alternating voltage, so when primary winding is excited by an alternating voltage, it circulates an alternating current. Okay, carefully listen to this. When primary winding is excited by an alternating voltage, that is supply voltage, it circulates an alternating current. So this current produces an alternating flux. Okay, this current produces an alternating flux, that is phi, which completes its path through core, common magnetic core, as shown in the diagram. Okay, shown in the diagram. Okay, thus an alternating flux links to the secondary winding. Okay, links to the secondary winding. As the flux is alternating, according to Faraday's law of electromagnetic induction, mutually induced EMF, mutually induced EMF gets to develop the secondary winding. So if now load is connected to the secondary winding, this EMF drives the current through it. Okay, thus there is no electrical connection between the two windings. If you observe the transformer, there is no electrical connection between the two coils, that is two windings, that is primary and secondary. So electrical energy gets transferred from primary to the secondary. Okay, so this is the principle of transformer. Okay, and coming to the construction of transformer, so actually we have I will tell the two conditions. So two topics. One is for the construction of basic transformer, and then I am going to explain the construction of single phase transformer also. Actually in our syllabus we have to discuss the construction of single phase transformer. So before going to that one, I am going to discuss the construction of transformer. So there are two basic parts of transformer. Okay, there are two basic parts of transformer. One is magnetic core and another one is winding or coil. Okay, winding or coil. So here the core of the transformer is either straight or rectangular in size. Okay, the core of the transformer is either straight or rectangular in size. So it is further divided into two parts. And the core of the transformer is further divided into two parts. So first one is the vertical portion on which coils are wound is called limb. So the vertical portion on which coils are wound is called limb, while the top and bottom horizontal portion is called yoke of the core. Actually we have the two portions, one is vertical portion and one is horizontal portion in the transformer, in the core of the transformer. The vertical portion on which the coils and the winding. Okay, on which the windings are wound is called limb, and while the top and bottom horizontal portion is called yoke of the core. Okay, so this is the construction of transformer. So on the left side we have the horizontal connection. We have that one is yoke, and the vertical portion is called a limb. Okay, so I already indicated with the arrow mark. So okay, the horizontal portion indicates the yoke, and the horizontal portion is called limb. Okay, next on the right side we have the another construction. So it consists of I-type lamination and L-type lamination. I-type lamination and L-type lamination. these construct joints, these construct joints, you observe the diagram. Okay, here I'm giving some dark color, so that one is known as the joint. Okay, those are also known as I-type lamination and I-type lamination. Okay, in that one we have the joint, which is connected both things. Okay, this is the construction of transformer. And the core is made up of lamination. Actually, the core is made up of lamination because of laminate type of construction, eddy current losses get minimized. So actually, we have different types of losses. So, but here, because of laminate type of construction, eddy current losses get minimized. That's why we are using the lamination to the core. The core is made up of some lamination because to reduce the eddy current losses. So actually, this eddy current loss concept explained in the DC motors also. Okay. Next, so generally, high-grade silicon steel laminations are used for the core, main core of the transformer. Okay. Generally, high-grade silicon steel laminations are used for the 0.3 to 0.5 thickness are used. So these laminations are insulated from each other. These laminations are insulated from each other by using insulation like varnish. So varnish is one type of lamination. Okay. Here we are using the lamination or varnish. So laminations are overlapping so that to avoid the area for the joint. So in the previous diagram I showed the laminations are overlapping. That means it is jointed so that to avoid the area for the joint. If we have a gap, we have some problem. To overcome the problem, so laminations are overlapping so that to avoid the area for the joint. So for this generally L and I-shaped laminations are used. That is also already shown the diagram. So this one. So this is the diagram explaining. Okay. Next, we have different cross-sectional areas, cross-sections in the transformer. So these are just some different cross-sections. One is rectangular shape, another one is square shape, another one is cruciform, and the third one is separate cruciform. Like we have different cross-sections in the transformer. So the rectangular shape cross-sections are used for small transformers, and the remaining shape cruciform and cruciform cross-sections are used for large transformers. Okay, these are the different cross-sections we are using in the transformer. Okay. So the cross-section of the link depends on the type of the coil. You already know this point. Okay, the cross-section of the link depends on the type of coil to be used either circular or rectangular. Okay, the different cross-sections of link practically use the stored in this diagram. So already discussed this diagram. Okay. Next we have staggering in transformer. So why we are using this staggering in the transformer means to avoid the high reluctance at the joint. To avoid the high reluctance at the joint, the alternate layers are stacked differently to eliminate the joint. Okay, to avoid the high reluctance at the joint. So the alternate layers are stacked differently to eliminate the joint. This is called staggering. So the butt joints are staggered in alternate layers. So if you observe this diagram, we have 4 types and arrangement of butt joints. So in the 4 types, we have first, third, fifth layers butt joints. So if you observe the diagram, I am taking a rectangular shape. Both 2 rectangular shapes So one is inserted into another. Okay, in that one we have some joints. So this connected to the one end of the rectangular shape and another one is connected to the other end of the rectangular shape. So those are the butt joints. Butt joints. Butt joints. Okay. And next, on the top of this one also we have the perfect butt joints. That is second, fourth, and fifth layer. Second, fourth, and fifth layer like that. And on the right side given cell type. So here also we are using the butt joint. Okay, on every corner. On every corner we are using the butt joint. In the cell type also we are using the two diagonals. Okay. So one first, third, fifth layer and second, fourth, fifth layer. And coming to the arrangement of butt joints, the arrangement of the butt joints are like this. So if you use different rectangular shape, so the butt joints are like this. Okay. Here we are using one core, so the cores are joined by the butt joint. Okay. So this is the arrangement of butt joints. And next coming to the construction, that means advantage of staggering in the transformer. Why we are using the staggering in transformer? So to avoid the continuous air gap. So to avoid the continuous air gap in the joint, we have to use staggering, and the reluctance of 90 circuit gets reduced. So by using the staggering, the reluctance of 90 circuit gets reduced. Iron at this point. And next, the continuous air gap reduces the mechanical strength of the core. So the continuous air gap reduces the mechanical strength of the core. Okay. Next, the strengthening helps to increase the mechanical strength of the core. Increase the mechanical strength of the core. And next, coming to the types of winding. Coming to the types of winding. So the coils used are wound on the links are insulated from each other. Okay, the coils used are wound on the links. Okay, and are insulated from each other. So in the basic transformer, the two windings wound are shown on the two different links. Okay, actually we have one transformer. The transformer consists of two windings. One is primary winding and another one is secondary winding. The primary and secondary windings are placed on the two different links. But both are placed on the 94 only. Okay. So that is primary on one limb and by secondary on the other limb. But due to this leakage flux increases. The leakage flux increases, which affects the transformer performance badly. Okay. So similarly, it is necessary that the winding should be very close to each other to have high mutual inductance. Okay. Similarly, it is necessary that the winding should be very close to each other to have high mutual inductance. And to achieve this, the two windings are split into number of coils and wound adjacent to each other on the same limb. Okay, and wound adjacent to each other on the same limb. So this is one cylindrical concentric coil. Okay. So a very common arrangement is cylindrical concentric coil in the concept of the transformer. So the diagram is shown in this one. So here we have core and two windings. So each consists of HV and LV. So HV is high voltage, LV is low voltage. Okay. So here both windings are same limb. So if you observe this one, both windings are in the same limb. Why? Just to avoid the leakage flux. That's why we are using the cylindrical concentric coil. Okay. Cylindrical concentric coil. Okay. A very common arrangement is cylindrical concentric coil that is shown in the diagram. Okay. So if you observe this, we have two limbs, but here the two windings are placed on the single limb. Okay. Why? Because to avoid the leakage flux in the transformer. Okay. Next, coming to the concept of transformer, the two cylindrical types. So first, cylindrical coils are used in four types of transformers. Okay, first cylindrical coils are used in the four types of transformers. Okay, these coils are mechanically strong. Okay, these coils are mechanically strong, and these are wound in helical layers. Okay, these are wound in the helical layers, and the different layers are insulated from each other by paper, cloth, or mica. Okay, so different layers are insulated from each other by paper, cloth, or mica, and the low voltage winding is placed near the core from ease of insulating from the core. Okay, the low voltage winding, that is LV winding, is placed near the core from ease of insulating from the core, and the high voltage is placed upwards. So LV and HV. So after the lower LV winding, we have to place the HV winding. Okay. After that, and the other type of coil which is very commonly used for the cell type of transformer is sandwich coil. So for the core type transformer, we are using the cylindrical concentric coil, and for the cell type of transformer, we are using the sandwich coil. Sandwich. Okay. So I will discuss the sandwich coil. So actually each high voltage portion lies between the two low voltage portions. Sandwich in the high voltage portion. Okay, each high voltage portion lies between the two low voltage portions. Sandwich in the high voltage portion. Okay, so such subdivision of windings into small portions reduces the leakage flux. Okay, this is one way to reduce the leakage flux. One is staggering and another one is visible. So such subdivisions of windings into small portions reduces the leakage flux. Next, higher the degree of subdivision, smaller is the reactance. This is one point. Okay, higher the degree of subdivision, smaller is the reactance. So the sandwich coil I will show in the next diagram. So the top and bottom coils are low voltage coils. So in the sandwich coil, the top and bottom coils are low voltage coils. So all the portions are insulated from each other by paper. Okay, all the portions are insulated from each other by paper. This is the sandwich coil. Okay, this is sandwich coil arrangement. So this one, so on the right, on the left and right we have one rectangular shape. So in this one we have different shapes. Okay, that is the rectangle only. So in this one we have low voltage and high voltage. Like this in dominating diagram, we have the conventional LV, HV, LV, HV and LV, HV. Okay. And coming to the concept of single phase transformer. So up to now we discussed about the construction of basic transformer, and now I am going to discuss the construction of single phase transformers. Okay, so the various constructions using for the single phase transformers are, one is core type and another one is cell type. So in the previous class I discussed about the core type transformer and cell type transformer, and now also I am going to discuss the core type transformer and cell type transformer in this one. Okay, so first I will take the core type transformer, and another one we have the berry type also. So in the previous class I discussed about core type, cell type only, but here in this one, in the construction of single phase transformer, we are going to discuss core type, cell type and berry type. Okay, so first I will discuss the core type transformer in the construction of single phase transformer. So the core type transformer has a single magnetic circuit. So I will show the diagram. After that you will understand this one. So the core type transformer has a single magnetic circuit. So in the core type transformer, the core is rectangular having two links. Okay, the core is rectangular having two links, and the winding ends up with the core. So in the core type transformer, the winding ends up with the core. Okay, and as mentioned earlier, the coils used are cylindrical type. So previously I discussed the transformer. In that one I discussed about cylindrical concentric coil. So that's why in the core type transformer, the cylindrical type of coils are used. So as mentioned earlier, the coils are wound in helical layers with different layers insulated from each other by paper or metal. So this one is already discussed in the basic transformer construction. So in this one, both the coils are placed on both the links. Okay, here we are using two windings or two coils. These two coils are wound on the both the links. Okay, here the low voltage coil is placed inside and near to the core. The low voltage coil is placed inside and near the core, and while the high voltage coil surrounds the low voltage coil. Okay, while high voltage coil surrounds the low voltage coil, and here the core is made up of large number of steel laminations. The core is made up of large number of steel laminations. Okay, next. So in the construction of the transformer, so in the core type, as the windings are uniformly distributed over the two links, the windings are uniformly distributed over the two links, the natural cooling is more effective. So the previous class I discussed about the cooling of the transformer. Okay, so let me distribute the natural cooling. Okay, so in this one, as the windings are uniformly distributed over the cooling, the natural cooling is more effective, and the coils can be easily removed by removing the laminations of the top of the yoke, and because of maintenance. And next, I will show the diagram. It shows the schematic representation of the coated transformer, and another diagram shows the view of actual construction of the coated transformer. I will show the diagram. So this is the coated transformer. On the left side we have the representation of the transformer, and on the right side we have the construction. So in the coated transformer, the representation is like this. So actually in any type of transformer, the representation like this only. Okay. So the rectangular shape is known as the magnetic core of the transformer. So to the core we are using the two coils or two windings. So on the left side we have the turn. So the one is called as primary winding. On the left side we have another winding which is named as there is a secondary winding. So actually the primary winding is connected to the AC supply. Why the AC supply is connected to the primary? The transformer is a alternating side. The transformer is works on the AC supply only. Okay, that's why the primary winding is connected to the AC supply, and the secondary winding is connected to the load. The secondary winding is connected to the load. So in the windings and the winding core, we have some dotted lines. Okay, so those dotted lines we also call it flux or magnetic flux lines. So this flux is travels through these two windings. So and we have the split. So one winding is connected to the one limb and another winding is connected to the another limb. And coming to the construction, so this is the construction of the core type transformer. So if you observe, we have LV and HV windings, and LV and HV insulation and one core is there and two windings is there. So this is the core type construction. So if you observe, the windings are wound, that means the windings are enclosed in the core of the transformer. Okay, so this is the construction and representation of the core type transformer. And coming to the second one, that is shell type. So in the shell type transformer, it consists of a double magnetic circuit. So the core type transformer consists of single magnetic circuit, but the shell type transformer consists of double magnetic circuit. And the shell type transformer has 3 limbs. Okay, so actually the core type transformer consists of 2 limbs, but the shell type transformer consists of the 3 limbs. That means the core. So here both the windings are placed on the central limb. Okay, both the windings, the two windings are placed on the central limb. The core intersects most part of the winding. So in the core type, the windings intersect the core, but in the shell type, the core intersects most part of the winding. So the coils used are generally multi-layer disc type. The coils used are generally multi-layer disc type or sandwich coils. So as mentioned earlier, each high voltage coil is in between two low voltage coils. Okay, and low voltage coils are nearest to top and bottom of the yoke. So I already showed that one, and I will discuss earlier in this session also. Okay, that means each high voltage coil is in between two low voltage coils, and low voltage coils are nearest to the top and bottom of the yoke. Okay. Next. So in the shell type, the core is laminated, and by arranging the laminations of the core, the care is taken that all the joints are alternate layers are staggered. That is, by this we reduce the high reluctance, and there is no area between the joints. That's why there is a staggering. So by arranging the laminations of the core, the care is taken that all the joints are alternate layers are staggered, and this is done to avoid narrow area of the joints and traveling in the system right to the cross section of the core. Okay, this is done due to avoid the narrow area of the joint and right to the cross section of the core. Such joints are called overlap or imbricated joints are called overlapped imbricated joints. Next, generally for very high voltage transformer, the cell-type construction is preferred. Generally for very high voltage transformer, the cell-type construction is preferred. So as the windings are surrounded by the core, the natural cooling does not exist. So as the windings are surrounded by the core, the natural cooling does not exist. But in the core type, the natural cooling exists. But in the cell-type, the natural cooling is not exist. Why? Because here the windings are surrounded by the core. So in the core transformer, the windings, the core is surrounded by the windings. Okay. So for removing any winding for maintenance, large number of laminates are required to be removed. So for removing any winding for maintenance, large number of laminates are required to be removed. So next, here I will show the diagram. It shows the schematic representation of the cell-type transformer and the away view of the construction of the cell-type transformer. So in the representation, actually we have 3 links. Actually, the cell-type transformer we have the 3 links and 1 magnetic core. So actually we have a single magnetic core, but in the cell-type transformer we are using the 3 links. Okay, but here the windings are wound on the central link only, central link. So that is the 2 side links we have and 1 central link. But in the cell-type transformer, the windings, both the windings are wound on the central link only. But the flux is traveling like this. Okay, the flux is traveling like this in the cell-type transformer. And coming to the construction, so in the cell-type transformer, the winding ends up in the core. The winding ends up in the core. Here it consists of the HV winding and LV winding. That is high voltage winding, low voltage winding like this. Okay, so this is the construction and representation of the cell-type transformer. And coming to the next one, that is B.Tech transformer. So actually this B.Tech transformer has distributed banding circuit. So in the core we have single banding circuit. In the cell we have double banding circuit. In this core of B.Tech we have distributed banding circuit. And the number of independent banding circuits are more than 2. Okay, the number of independent banding circuits are more than 2. And core construction is like spokes of a wheel. I will show the diagram after you will understand this one. So the core construction of the B.Tech looks like spokes of a wheel. So like if you have a bike, that we consider spokes. Okay, like that the construction of the B.Tech is also same. So otherwise it is symmetrical to that of cell-type. Okay, otherwise it is symmetrical to that of cell-type, similar to that cell-type. Okay, next diagram can be shown the diagram. So this is the B.Tech transformer. So see this one. So it is looking like a spokes of a wheel. Spokes of a wheel. It consists of this core and it consists of LV and HV winding. Okay, LV and HV winding. This is the B.Tech transformer. And next. So the transformers are generally kept in tightly fitted sheet metal tanks. Okay, the transformers are generally kept in tightly fitted sheet metal tanks. So if you observe in your street, in every street we have one transformer. So the transformers are generally kept in tightly fitted sheet metal tanks. So those tanks are constructed of specified high quality steel plate sets. Specified high quality steel plate sets formed and welded into the rigid structure. Okay, formed and welded into the rigid structures. And all the tanks are painted with a solution of light blue starch. Okay, all the drawings are painted with a solution of light blue starch, which comes dark in the presence of oil. Disclosing within the minute leaves. Okay, minute leaves. And the tanks are filled with the special insulating oil. The tanks are filled with the special insulating oil. So the entire transformer assembly is immersed in the coil. Okay, the entire transformer assembly is immersed in the coil. The oil comes from functions. One is keep the coil cooled by circulation. Keep the coil cooled by circulation, and it also provides the transformers an additional insulation. The coil provides the transformer and additional insulation. And next, so the oil should be absolutely free from alkalis, that means sulfur and especially from moisture. So the oil should be absolutely free from the alkalis, sulfur and especially from moisture. And the presence of very small moisture lowers the direct strength. So the presence of very small moisture lowers the direct strength of the oil, affecting its performance badly. That's why you have to take care of the oil should be absolutely free from the alkalis. Okay, next, hence the tanks are sealed airtight. Why? Because to avoid the contact of oil with atmospheric air and moisture. Okay, the tanks are sealed airtight. Airtight, that means there is no air gap in between. Why? Because to avoid the contact of oil with atmospheric air and moisture. And in large transformers, the chambers called breakers are provided. So the breakers prevent the atmospheric moisture to pass onto the coil. So the breakers prevent the atmospheric moisture to pass onto the oil. Next, the breakers contains the silica gel crystals which immediately absorb the atmospheric moisture. Okay, the breakers contain the silica gel crystals which immediately absorb the atmospheric moisture. Okay. And due to long and continuous use, the sludge is formed in the oil, which can contaminate the oil. So due to long and continuous use, actually the transformer is used for the long term and continuous use, the sludge is formed in the oil, which can contaminate the oil. Okay. And to keep such sludge separate from the oil in one tank, an airtight metal drum is provided. An airtight metal drum is provided, which is placed on the top of the tank. That one is called conservator. So in the conservator, we are separating the oil from the main tank, that means to overcome the sludge problem. Okay. Next, coming to the comparison of the core-type and cell-type transformers. So in the previous class also I discussed the comparison between core and cell-type. So in the core-type, the winding enters into the core, and in the cell-type, the core enters the most part of the winding. And the cylindrical type of coils are used in the core-type, and generally multi-layer disc type of standard coils are used in the cell-type. In the core-type, cell is constantly concentrated coils are used. In the cell-type, we are using multi-layer disc type standard coils are used. And in the core-type, the windings are distributed. The matching cooling is more effective. And in the cell-type, the windings are surrounded by the core. The matching cooling does not exist. And in the core-type, the coils can be easily removed from maintenance point of view. But in the cell-type, removing any windings for the maintenance, large number of laminations are required to be removed. This is difficult. And the construction is preferred for low voltage transformers in the core-type transformer. The construction is preferred for low voltage transformers. And in the cell-type, the construction is used for very high voltage transformers. And it has a single magnetic circuit. The core-type transformer consists of single magnetic circuit, and the cell-type transformer consists of double magnetic circuit. And the core-type in the single phase type, the core has two rings. In the single phase type, the core has two rings, and the cell-type in the single phase type, the core has three rings, two side rings and one central ring. But in the core-type, we have two rings that are based on size. The size is the connected side ring. So that is the construction of basic transformer and construction of single phase transformer. And now I am moving to the next topic, that is operation of single phase transformer. It is similar to the working principle of transformer only, but here I explained in different ways, that is in the separate way. So you already know that the transformer is a static device which changes the alternating voltage from one level to another. You already know this one. And here I will show the diagram. This is the connection diagram of the transformer. You already know the transformer consists of one magnetic core and it consists of two coils. One is the primary coil and another one is the secondary coil. It is also the primary winding and secondary winding. The windings which are connected to the supply, that is on the left side of this diagram. That one is called primary winding, and the winding which is connected to the load, that one is called secondary winding. And in between these windings we have some dotted line, that one is called a flux And in the primary winding we have primary voltage V1 and the primary current I1, and in the secondary winding we have primary current and primary voltage, and this iron core, and this iron core is laminated from insulated because to reduce the eddy current losses in the core. And as you can see, it consists of a magnetic core. It consists of a magnetic core or iron core and two distinct windings wound over the core, and two distinct windings are much primary and secondary windings. And the two windings are two independent electrical circuits. The two windings are two independent electrical circuits, whereas the core forms a magnetic circuit which is common to both the windings. Okay, whereas the core forms a magnetic circuit which is common to both the windings. And the basic principle of transformer is the mutual induction between two circuits that is linked by a common magnetic circuit. And if one winding is connected to AC supply, an alternative flux is established in the core. An alternative flux is established in the core, and most of the flux links with the other winding. And this produces a mutual linkage between the induct winding. Okay, this produces a mutual linkage between the induct winding. So these all are valid in the working principle of transformer and repeating those things in the operation of the transformer. Both are same. Okay. So if the circuit of the secondary winding is closed, that is when it is connected to the load, a current flows in it. Okay, current flows in it, and therefore electrical energy is transferred from the first winding to the secondary. Okay, hence the input and output frequency is the same. There is no difference in the frequency. The first winding, which is connected to the AC supply, is not primary winding, you know this one. Whereas the other winding to which the energy is transformed is not secondary winding. Okay, so the transformer being a stationary device is also called a static transformer. It also called a static transformer. And coming to this one, the single phase transformer is an electronic component. So the single phase transformer is an electronic or electrical component that operates on a single phase alternating current. As the voltage cycle occurs within a unified time phase, as the voltage cycle occurs within a unified time phase, and it is commonly used to load long distance signals for both light commercial and residential electronic devices. Okay, it is commonly used to load long distance signals for both light commercial and residential electronic devices. Here are the steps involved in this block. Those are first one is external AC power generates an alternating electromagnetic field. External AC power generates an alternating electromagnetic field through the primary winding. And the electromagnetic field collapses in the iron core, linking the flux in both the windings. Okay, and the power is induced through the secondary winding, connected to a load at 60 edges. Power is induced through the secondary winding, connected to a load at 60 edges. Okay. Next, so Faraday's law determines the induced voltage and ampere. So you know this Faraday's law determines the induced voltage and ampere, which can be modified by the nature of the primary and secondary winding. Okay, and next external radio interference, that is RFI, is created to protect electronic equipment. So RFI is created to protect electronic equipment, and primary and secondary windings are usually made of insulated copper wires and must be isolated from the iron core, which has high permeability. And the high voltage that can be used for induced is controlled by utility companies and municipal regulations. Okay, so before deciding on whether to use induced or single transformer, you should check the manufacturer specification on using the electronic components or consult with an electrical expert. Okay, so this is the operation of the single transformer. And commercial applications of single transformer. So these are used step down localized power distribution and single sets to regulate voltage, and in the low voltage electronic devices, and step up power in home inverters and non-urban areas where electrical demand is lower. Non-urban areas where electrical demand is lower. And commercial and residential lighting and heating equipment. In all these applications, we are using single transformer. Okay. Thank you for watching this video. In the next class, I am going to discuss another topic of the transformer like that.